So this problem asks us to find the resistance in R. So what we do is we do a Kirchhoff's rule for this loop right here, find the current in that, which is going to be I1. So what we do is 25 minus 5I is equal to 10 plus 30, so 40 I1, because that's the equivalent resistance of this line right here. And so we need to find what I is, so we can do that by doing V over the equivalent resistance of the whole circuit. So the equivalent resistance of the whole circuit is going to be the equivalent resistance of this, which is 10 plus 30, which is 40, and the equivalent resistance of this, which is 10 plus 30 equals 40. And then we find the equivalent resistance of this part right here, so which is going to be 1 over 40 plus 1 over 40 equals 1 over the equivalent resistance of just this part, not the whole circuit. And so that's going to be equal to 1 over 20, so the equivalent resistance of this part is just 20 ohms. And when you add that to this, because this is in series with this equivalent resistance right here, so you get the total equivalent resistance to be 5 plus 20, which is equal to 25. And so V is also equal to 25, and the equivalent resistance is 25, and so this is equal to 1 ampere, which is equal to I. When you plug that into this equation, you get 25 minus 5 equals 40I1, and so this equals 20. 20 divided by 40 is equal to 1/2, so 0.5 amperes is equal to I1. So part B asks us to find the current in resistors R again, except with the capacitor involved. And in the problem it says that the currents in the circuit and the charge on the capacitors reach constant values. So once the charge reaches a constant value, there is no current going through this capacitor, and therefore the circuit is pretty much the equivalent of what we had in part A. So the resistance of, or the current in resistor R is going to be the same value as in part A, which is just I1 is equal to 0.5 amperes. Okay. To find the charge on the capacitor, we use a Kirchhoff's rule loop over here. And so the equation will be negative 30 I2, because it's in the direction of the current, plus Q over C, plus 10 I1, because it's in the direction opposite of the current. That's why it's a plus, equals 0. And then we know that according to the junction rule, I splits into I1 and I2, so I, which equals 1 as from part A, because there's no current running through the capacitor, is equal to I1, which is 0.5 as determined by from part B, plus I2. So I2 is also equal to 0.5. And when you plug in 0.5 for I2 and I1, you get negative 15 plus 5 plus Q over, and C is given as 10 microfarads, so 10 times 10 to the negative 6 is equal to 0. And this simplifies to negative 10, so Q is equal to 100 times 10 to the negative 6 coulombs, which is equal to 100 microcoulombs. So then for part D, I defined the main current to be I, current through resistor R to be I of R, current through the 30 ohm resistor over here to be I1, the current over here to be I2, and the current in this resistor to be I3, and the current across the inductor to be I4. So how we do this problem is we have to recognize that these voltages are equal to each other and these voltages are equal to each other. So 10 times IR is equal to 30 times I3, and 30 times I1 is equal to 10 times I2. And then we use it junction rule to find out that I equals IR plus I3. And since IR is equal to, well, since 10 IR is equal to 30 I3, you know that I3 is equal to 1/3 of IR. So this is equal to IR plus 1/3 IR. And so this is equal to 4/3 IR. So IR is equal to 3/4 of the main current. And to find the main current, we have to recognize that to find the equivalent resistance of this whole thing right here, these resistors are also in parallel, just like these resistors. So what you do is, to find the equivalent resistance, you do 1/3/30 plus 1/30, so that this is 3/30 instead of 1/10, just because I just made it the same denominator, and plus, well, 1 over this, because that is what the equivalent resistance is, and then plus 1/1/3/30 plus 1/30 plus 5, because that's going to be in series with this part, is equal, which equals 20 ohms. So we can find this I by using that. So this is the equivalent resistance of this whole circuit. So you do V over R is equal to I. So it's equal to 25/20, which is equal to 5/4 amperes. And if you plug that back in over here, you get 3/4 times 5/4, which is equal to 15/16 amperes. So over here, for problem E, we use junction rules to find that IR is equal to, IR is this one, is equal to I4, which goes this way, plus I1. And I4 is going this way because these voltages have to be the same since they are in parallel. And since V over R is equal to the current, this current is going to be lower than this current because it's V divided by 30 and this is V divided by 10. So this is the junction rule for this junction. And then we use the junction rule for this junction. So we get I3 plus I4 is equal to I2. I4 being this one, I3 being this current, and I2 being this current. And then we have to recognize that these voltages are the same, so 10 times IR is equal to 30 times I3, and over here 30 I1 is equal to 10 I2. And then, so we know that 1/3 IR is equal to I3, and we know that 1/3 I2 is equal to I1. When we plug these into this equation, for this equation we get IR is equal to I4 plus 1/3 I2, and over here we get I2 equals 1/3 IR plus I4. And you don't substitute out the I4s because that is the current that you're solving for. And now you can plug this into here as I2 because that's what I2 is equal to. So you get IR is equal to I4 plus 1/9 IR plus I4. So we simplify this equation, so you subtract 1/9, so you get 8 out of 9. IR is equal to 4/3 I4. Then when you take this to this side, so 3 out of 4 times that, you cross out 2, cross out 3, so 2/3. Then you have to remember that IR from part B is equal to 15 out of 16. So 2/3 times 15 out of 16, and that cancels out to 8 and 5 is equal to I4. I'll just rewrite it again, is equal to 5/8 amperes.